Alright guys, so we've been taking time in class looking at forces and looking at how those forces act on objects, and then we were drawing force diagrams or free body diagrams to show how different forces are acting on one object. You guys are getting pretty familiar with this. You're doing alright with it, showing which forces are acting in which direction, and most of the time being able to identify which forces are acting and which aren't. Okay, at this point what I'd like to do is introduce a couple of things that will help you to fine-tune these force diagrams or free body diagrams that you're doing. Okay, the first thing is that I would like for us to pay attention to our vector lengths. Alright, now we know that vectors have both magnitude and direction. Now the direction part's easy because you just draw the arrow pointing in whatever direction the force is. Okay, now the length corresponds directly to the magnitude, right? So a force that's twice as big should have a vector that is twice as long. And so I'd like for us to pay a little bit closer attention to that. Secondly, just because some of us in the class have the tendency of just throwing in a normal force whenever you want a normal force just because you think you need it or because we always have one or whatever reason, I'm going to have you identify what is causing your normal force. Okay? A normal force is not magic, as Max says. It's not something that just appears when we need it, or that's just always there. It's something that occurs because of contact between two objects, right? It's a contact force. So in order to have a normal force, something has to be contacting the object that we're looking at. And so we'll consider that and we'll look at that as we're drawing forces. Remember, we only have three contact forces: tension, friction, and the normal force. Okay, a normal force is just any other push between two objects as they contact. So let's look at this situation where I will be throwing a ball straight up in the air. Okay, so it goes straight up, comes straight down. You know it's me because I'm tall and skinny and just plain good looking. So here's our ball that's flying up in the air, coming down. We're going to look at 5 specific positions: A, B, C, D, and E. Okay, point A is during the throw. Okay, so during the actual throw of the ball. Point B is as my ball is traveling up through the air. Point C is at the very maximum point. We know if we throw the ball straight up in the air, it stops for an instant or a fraction of an instant and then comes back down. At point D, it's coming down, and then point E is during the catch. Okay, so it's actually physically during that motion of catching the ball. So not after the catch, not before the catch, but during it. Okay, so what I would like for you to do is take some time and draw a force diagram for each of those 5 positions. Maybe pause the video, because I'm going to go straight into it. Pause the video, draw your force diagrams, and then check it. Okay, hopefully now you've taken the time to draw your own force diagram, so now let's check it and talk about it. And I'm going to be including the vector length and identifying the normal force as we do that. Alright, so at point A, we know gravity is pulling down. Okay, and we also know that as the ball is moving up through the air, it is rubbing against air particles, and so as it's moving up, friction is going to oppose that sliding of the ball through the air, and so friction is going to be going down. Now air friction is going to be considerably less than the force of gravity, so I'm going to put a smaller arrow there. Alright, now also at point A, I'm touching the ball, which means there's definitely a contact force between my hand and the ball. That is a normal force. Okay, now that force, if we want the ball to go upwards, that force has to be bigger than the force of gravity and the frictional force, which are down. And so I know right off that the normal force of my hand is going to be going up, pushing the ball up, and it's big. Alright, so that's what I've shown here. Let's go on to point B. At point B, again, we have the force of gravity. We're going to have the force of friction, right? Because the ball is going up through the air, sliding against air molecules, so the friction is going to be pushing against the motion, which is going to be down. And do I have any other forces? No, I don't. Now, some of you may be saying, yeah, but the ball's going up. Something had to push it up. Well, yeah, but that was before. In order for there to be a force now, something has to be contacting it now. Newton's first law says that if it's moving, it will continue to move because it already is. And so it's going up because it already was before, because there is a previous force, not because there's one now. Right now, we already know the acceleration is downwards because it's going up and slowing down. So that means the forces have to be going down right now. All right? So there is no force up at this point. All right? Let's go on to C. At point C, you've still got the force of gravity. Okay, just like that. But since it's at rest for that instant up at the top, we know there's no friction there because it's not rubbing against the air. On to point D. Force of gravity again. And since now it's moving down, now the air friction is going to be up. All right, on to point E. You've got the force of gravity down. Note that all my force of gravities are about the same length. I messed up on this one. It's a little bit shorter, but they're all about the same length, showing that they're all the same. Gravity is constant. Okay, force of air friction is still up, but here, as I'm catching it, my hand again is touching the ball. And as my hand is touching the ball, that means that there has to be a large normal force of my hand on the ball as it is stopping the ball from going down, and so you can actually feel that force. Alright, does that make sense? Hopefully you got these things, and if not, hopefully you understand why they are as they are. Okay, let's go on to another example where I'm going to show you the next two things I would like for you to consider. Alright, so the next two things are going to not be dealing with the free body diagrams themselves, but actually with the equations that we write in conjunction with this, the horizontal and vertical equations. We've got a toy duck that's being pulled at a constant velocity by a string at an angle of 45 degrees. So let's draw the free body diagram on the duck. So here's our duck. Beautiful duck. I know I'm an awesome drawer. And then we've got the force of gravity, which is going to be pulling down on it. We've got the tension, which is going to be pulling up at 45 degrees. Okay, then I've got a normal force which is pulling up. Now I've already got the tension pulling up a little bit, so I know that the force of the normal force isn't going to be quite as big as gravity because those two, the normal force and tension, are both pulling up. So I'm going to make that one a little bit shorter. Now again, we can't just call it the normal force. This is the normal force of the ground. I know the ground is pushing on it. Ooh, ground is definitely spelled with an N. I know the ground is pushing up on it because it's touching the ground, and the ground therefore will exert a force on it which is perpendicular to the surface, so straight up. Now obviously if I'm pulling it along this way and it's going at constant speed, there has to be a force going the other way, which most of you will already identify as the force of friction. Okay, so there we go. We've got our free body diagram. We've identified all the forces. Now prior to this, I allowed you to get away with just writing that the sum of the horizontal forces is equal to the horizontal tension plus the force of friction. And I allowed you to get away with saying that the sum of the forces in the y direction is the tension in the y direction plus the normal force of the ground plus the force of gravity. Now, what I would like for us to do to kind of fine-tune this is number 1, which is going to be number 3 on this video, is I would like for us to do the trig, which is associated with the components, to relate those components to the original force. Okay? In other words, I don't want to write down tension X. I want to write down how I can get that from the tension overall. Okay? Secondly, I would like for us to look at the plus or minus, whether the force is a positive or negative force. Okay, we know that there's a direction for each force. Before we just said, yeah, one of these will be positive, one will be negative. But I would like for us to show that in our mathematics, to show that we understand which forces are positive and which forces are negative. So let's look first at the trig. So let's look at the tension. So I'm going to redraw the tension force over here. Okay, and we're looking at the horizontal component, and we're looking at, that's an X, and we're looking at the vertical component. So if I'm trying to find the horizontal component, and I'm trying to relate that to the overall tension, then I'm going to be using the angle, which is 45 degrees, and that is adjacent over hypotenuse. So that will be the cosine. So cosine of 45 is equal to the adjacent over the hypotenuse. All right. Now, if I want to find out what Tx is, that means I need to multiply both sides by T, which means that T cosine 45 is equal to the tension in the x direction. And so that's what I'm going to put in over here. Okay, so I'm going to rewrite this as being tension cosine 45. Now that's positive because it's going to the right. And then the force of friction is going to the left. So I'm going to write that as being minus the force of friction. Yet now you'll see that all my forces here correspond directly to a force that I've written here. We're going to do the same thing with the y. Okay, so instead of writing tension in the y direction, that would be opposite over hypotenuse, so that would be sine. So sine of 45 equals the tension in the y direction over the overall tension. Multiply both sides by t, so t sine 45 is equal to tension in the y direction. So that means that is going up, right? That component is up right there, so that will be t sine 45. The normal force is going up, so that's positive, so plus the normal force of the ground. Now gravity obviously is going down, so that will be minus Fg. So hopefully that makes sense, and you can see how I put in the plus or minus and how we're going to use that. Also, hopefully you can see how we did the trig and made that associated. The point again of that is that now in my equation, all of these forces, T, force of friction, T, normal force, force of gravity, are these numbers that I have here. If you were given the tension as a number, you could now just plug that number in with the trig and you could find out what the numbers were. Okay, so there you go. Try to apply that in your homework tonight. Good luck.